Welcome back to Miss B Makes It Easier. I know we're moving right along with introducing the periodic table. This is what the periodic table looks like. You have starting with hydrogen and it ends with, it starts with hydrogen and it ends with nobelium. Okay, so this is what it looks like, and you have to get accustomed to seeing it, and you have to learn the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 elements. You have to learn them by heart, and you also have to learn their atomic masses. So you have to learn their atomic numbers, and you have to learn their masses. It'll make your life much easier in the long run. Okay, so moving right along. How does the periodic table help us in chemistry? The periodic table simplifies chemistry for us. It helps us to A. Identify patterns in the chemistry of elements, B. Formulate theories to explain these patterns, and C. Predict the chemistry of unfamiliar elements. In 1869, Mendeleev proposed that a definite relationship existed between the chemical properties of elements and their atomic masses. His observations made the periodic table what it is today. He even left gaps wherever the order of his classification suggested an element should exist there, even though it was not known. Amazingly enough, he correctly predicted the properties of these missing elements. Now remember, before in some videos earlier than this, I would have told you that there are about 92 naturally occurring elements, and in all we have found 103 approximately. In Mendeleev's time in the 19th century, they did not discover 92 elements, or 103. They didn't discover it. So Mendeleev, having foresight, right, knew that he didn't discover all of the elements, and there must be some more that he would not know about. And in doing so, he left the spaces for them that he couldn't account for. And that's why he's seen as so great, because he paved the way towards creating the periodic table. Okay? So of course, with every discovery, there are imperfections in that some of the atomic masses of some elements did not fit the pattern. These problems were later cleared up by Moseley in 1913. And I would dare you to go and look up what Moseley did in 1913 to clear up this problem. He did this by arranging the elements in the atomic proton number instead of their atomic masses. So basically, you could look up the whole story about Moseley, but what he did, what Mendeleev was doing was looking more at the masses and trying to place them in patterns based on the masses. But it was found that the proton number was of most importance, and that is how you would put them in order based on the proton electron count when the atom is neutral. So on the cover of this handout is a modern version of the periodic table. So you need to learn the symbols, the atomic masses, and the atomic numbers of at least the first 20 of the elements, hydrogen through calcium, which is what I showed you earlier. So the periodic table divides elements into horizontal rows or periods. And the periods refer to energy levels. Each time you move on to an energy level, there is a new period. So you refer to the period as the energy level. And the columns are referred to as the groups. And the groups refer to the valence electron count. So let's now explore the periodic table. So what I'm going to do, I'm going to put a schematic on the board, and I'm going to explain it as I go along. Okay, so just like what you would have seen on the front page, I'm going to do that. So here you have, it's just going to be an example. And if you notice, you have an asterisk and two asterisks. That is where the lanthanide series and the actinide series are fitted in. So those are fitted in at the bottom. Fit in at the bottom. And the only reason why they're not put together is because of spacing in a textbook, but in actuality, this is how the periodic table is supposed to look. It's just that they're disjointed for spacing reasons. And then we're going to put in the transition metals. And then from there, we're going to go back to what we have up here, and then bring it down. Between the lanthanide series, we have 2 periods going across. So this is 6 and 7, the 6th period, and this is the 7th period. So remember, periods going across. So periods are rows. So periods go that way. Okay? And so we go across here now in the transition metals. Coming across here, 2. Here. Okay. And then we have so that should make 7. 1, 2, 3, 4, 5, 6, 7. So this is the first period. The first period has in hydrogen and helium. Okay? So we're going to break it here. And then break here. And then from here now we have group 8. This is group 8. So the groups now, the groups go up and down. So they go up and down in columns. So this is group 1, GRP1, group 2, and then we're going to start here. So this is in this area you have the lantanides and the actinides. So lanthanide series, and they have the actinide series. So the lanthanide series is on top, and then you have the actinide series which is below. Okay? And so that is taken care of. Yeah, and then in this area now you have the transition metals. In this area is the transition metals. And basically this set and this set we don't really pay attention to in high school. This is the transition metals. Okay, and then now we have group 3. Group 3 starts with boron. This is group 3, GRP3, and then we have group 4, which starts with carbon, and group 5, which starts with nitrogen, and group 6, which starts with oxygen, and then group 7, which starts with fluorine. And then right here next to fluorine, we have neon. Okay? So, this is group 4. And we have group 5, 6, 7, and then we have 8. Right? Okay. So, that's pretty much how the schematic is so long. Good? Alright, so as we move along, I'm going to add stuff. So what do they mean by periods refer to energy levels? Well, with periods, so we have here periods go across, but groups, periods go across, back and forth, and groups are the ones that go up and down, correct? And so once we have that, with the period, we're going to talk about energy levels for period 1, for the first period, it will be something like this. You have your nucleus, and then you have your first energy level. Okay? Then you have your second period. So you have your nucleus, you have your first energy level, you have your second energy level. Third, once you start getting to the third energy level, it starts to get a little bit complicated, and so that's why we stop around this area. We don't, in high school, you stop around this area because after that, by the third energy level, you have subsets and all sorts of things, so you stop by then. Because remember, in the first shell can hold a maximum of 2 electrons. Maximum. That's the first shell. Could hold a maximum of 2 electrons. The second shell can hold a maximum of 8 electrons. And the third shell hold a maximum of 18 electrons. We start with 8 electrons first, and then you lead up to 10 electrons, which is another shell. So that is why we stop at 3, because it gets complicated after that. And so this is what we call energy levels. And if you look at it, the atomic radii starts to get bigger and bigger as you go down the group. So this hydrogen will be much smaller in size than cesium. Cesium, I think that is francium. Francium is the one that is right here. So this is much bigger than this. Okay, so the periodic table divides the elements into metals, non-metals, and semi-metals. Group 1 and 2 contain only metals. They are found on the left-hand side of the periodic table. So these two contain metals only. So this would only have your metals. These are all metals. These are metals here. But guess what? Group 3 is all metals as well, except for boron. And to remember that, you say boron is a moron. So boron is the only non-metal in group 3, so boron is a moron. Okay? Cool. Now group 1 is often referred to as alkali earth metals. So we write the word alkali in here, so these are alkali earth metals. And why are they called alkali earth metals? These metals are called such because they form alkalis when they react with water. That is, strong bases are capable of neutralizing acids. In group 2, the metals are referred to as alkaline earth metals. So these are alkaline earth metals. Okay? So group 2 elements are referred to as alkaline earth metals because these are derived from alkaline minerals such as slate, limestone, etc. that are naturally found in the earth. The oxides of these metals give basic alkaline solution. These oxides require very high temperatures to melt and can remain solid in fires. You could think of it as the earth, which remains solid in fires once the temperature is not too high. So group 3 contains metals with the exception of boron, like they would have said here. Group 7 is referred to as the halogens. So group 7, we call those the halogens or the halogens. And group 8, we call them the noble gases. And these are basically inert as in they don't react. At high school level, they don't really react. So all here, this is group 1, this is group 2, 3, 4, 5, 6, 7, 8, and they don't below as well, right? So group 7, you refer to them as the halogens, and group 8, you refer to them as noble gases. In the noble gases section, you'll find things like helium, neon, krypton, radon. In the halogen section, you will find things that rhyme, like fluorine, chlorine, bromine, iodine, astatine. So this is the section that rhymes. So you can call them the nursery rhyme section if you want. Or just remember they're halogens. Okay, so the diameter or the size of an atom is referred to as the atomic radii, right? So an atomic radii decreases across the period due to the greater nuclear charge affecting an attraction between the electrons and the protons found in the nucleus of the atom, right? So if you go from left to right, atomic radii decreases, and going down, atomic radii would do the opposite. Atomic radii would increase. And the reason why it increases is because as you go from top to bottom, from up here to down here, the amount of electrons in each of the atoms increase, and electrons are negative. And negative repel, so then they repel each other. And just like I would have shown you, demonstrated here, you will see that the rings start spacing out further and further. And as it spaces out further, the atomic radii will increase. And the radii meaning from the very center of the nucleus to the outermost shell. That's the radii between here and here. So the radii here in this depiction is much further away than the radii here and here. Okay, and this will be due to electron repulsion. So atomic radii increases due to electron repulsion, and atomic radii decreases going from left to right due to nuclear charge, right? So the increase of nuclear charge as we move across the period. Okay? And here we have a picture too in the notes, where you can see how small hydrogen is as compared to cesium. And hydrogen is bigger than helium here. They were almost the same size, but helium will be a little bit smaller because it has two protons and 2 outer electrons. Okay? Alright, so that is what you see. And if you look at it, lithium is much bigger than neon. And again, a question like this, you say, why is the atomic radii of lithium bigger than that of neon? Well, of course, because of nuclear charge. So, neon contains more protons in its nucleus than would lithium, and therefore the nuclear charge is greater on the outermost electrons. Okay? So you can use that. Electronegativity measures the ease with which an atom attracts the electrons in a covalent bond. And electronegativity belongs to the right side. These are electronegative, right? They are hungry for electrons because they have incomplete octets of about 7 and 6 and 5, because that is so. If you look at fluorine has let's go back to the front. Fluorine has 9 electrons, okay? And if you draw it out, you would see that, yeah, fluorine, this is fluorine in here. It's just acid nucleus to start with 2. So it says 9. So 9 electrons minus 2 will leave back with 7 electrons. And the second shell can hold a maximum of 8. But you have 7, so you have enough. You haven't met the 8 and you haven't surpassed the 8. So here we have 7 electrons. it wants to complete its outermost shell with an extra electron, so it is called electronegative. It's highly electronegative. Okay, it wants that, and it has a high nuclear charge, right? So it wants to complete it. So these are electronegative. So electronegativity increases from left to right. These elements on the left are known as electropositive. So electronegativity from left to right increases, and electronegativity increases going up. So fluorine is the most electronegative element in the periodic table. As you go up. Okay? So I'll just read it now. In general, small atoms have high nuclear charge, a high atomic number, and they have the highest electronegativities. So in general, small atoms with high nuclear charge or high atomic number have the highest electronegativities. Which set of elements are more electronegative? Non-metals or metals? Now note well, these are metals, everything in group 3 are metals except for boron, and then we start coming off as non-metals. So the non-metals, right, where you see carbon, nitrogen, oxygen, and fluorine and neon, those are non-metals. We're coming on to things that, you know, like gas in gaseous form. So those are the ones that are most electronegative, right? So electronegativity increases across the period from left to right. Okay? Electronegativity decreases are moving down the group, but I show that it increases as you go up the group, so of course it will decrease going down the group. Elements with high electronegativity values are oxidizing agents, and elements with low electronegativity values are reducing agents. Between the metals and the nonmetals are the elements that have some properties of both. These are called metalloids, and they're used to make semiconductors. N-type semiconductors and P-type semiconductors. N stands for negative type and P stands for positive type. We'll explore those later. Silicon, arsenic, boron, germanium, etc. are examples of metalloids. Now, I just want to say before I leave, I want to explain why hydrogen is where it is. Hydrogen can be found in group 1, and it can also be found in group 7 sometimes. So on some periodic tables, you will see they have hydrogen in the center here, right? And that's simply because with hydrogen, hydrogen has only one electron, and that one electron occupies an electron shell that can hold a maximum of 2 electrons. And so, see, hydrogen has 1 proton and 0 neutrons because it has a mass of 1. And that is the nucleus right there. In its outermost shell, the outermost shell holds that 1 electron, and that outermost shell can hold a maximum of 2 electrons. So sometimes when hydrogen reacts with something else and it takes on an extra electron, it takes on that extra electron. What happens is that it now acts like a halogen. Right? That is what halogens do. They take on an extra electron. For instance, like fluorine, remember we had 7 protons, and with fluorine, had 9 protons. With fluorine, the first would have 2, and the second shell would have 7. Right? And if you look at the comparison here, you would see that all fluorine needs is an extra electron to complete its outer octet, which can hold a maximum of 8. However, with hydrogen, it cannot help because its outer shell can only hold 2 electrons, which makes it open for fulfilling its duplet. In this case, it's a duplet because it only can hold a maximum of 2. Helium is in group 8 simply because, guess why helium is in group 8? Helium is in group 8 because it has 2 protons, 2 neutrons. Therefore, it has 2 electrons. Those 2 electrons have completed its duplet, and this shell can only hold 2 electrons, so therefore it is a noble gas. It is no longer ready to and willing to react with anything. It is complete. It is happy. Okay, and that is why it is in group 8, even though the rest of them would have a full octet of about 8. Okay? Alright, so thank you for listening, and see you in my next video. Alright, good night.